Good morning, everyone. Welcome to the second day of our dark matter workshop. So it is my pleasure to start our morning session. So the first speaker is Yvonne Albuquerque from the University of São Paulo, and she will tell us about the dark side experiment. Thank you.
Hello, is it working? Hello? Yeah, there it goes. So would start by thanking for the invitation, and I will talk specifically about analysis we did on dark side data that aims to understand the low dark matter mass region. Yeah, he gave it to me. So the dark side experiment is a liquid argon experiment where we have a double phase detector, which I will go through a little bit. So the data I'm going to talk about is on 530 days of data with the detector on the 50 mode. So this is one of the steps into a liquid argon experiment, and the idea here was mainly to test how well we could do with liquid argon. Here. So the idea here is we have a double phase time projection chamber, and this is a picture of our detector. The fiducial volume is 36 kilos. And the idea here is that you have the target is liquid argon, but we have on the top a small pocket of gas phase argon. So the idea is that your dark matter particle will come in, interact one of the argon atoms, and in this interaction, it will scintillate. So you detect the scintillation light with photomultiplier tubes here, and this is what we call the prompt signal. So, and we call it a S1 signal. Then we have an electric field around the detector from these coils here, and the electron field will make the electron that is ionized merge up and eventually get into the gas region. Here you will have some electroluminescence of the electron, which will be detected on the PMTs. This signal we call a S2, or an ionization signal. So the interesting thing is that with this prompt light, we can use pulse shape discrimination, which can allow us to discriminate electrons versus nuclear recoil, and I will explain this in a bit. And we have the difference in time of the S1 and the S2 signal will allow us to determine the Z position in the detector, and that also helps in the background rejection. And the light fraction that's on the PMTs will help us have pinned down the XY position. So for liquid argon, a very strong tool is this pulse shape discrimination, and this is described, I'll come back, I'll describe this later. So this is a picture of the TPC. So here we have liquid argon, this is the gas pocket, and we have 19 PMTs on the bottom and 19 on top. We have a field here that's a 200 volts drift field, so the electron will go up, and we have an extraction field that's much higher. So the backgrounds for WIMP detection came mainly from two sources. They can be electrons and gammas, and these are produced in the TPC around the detector in the cryostat, and they will mainly interact with the electrons of the argon atom. So in this sense, you have electron recoil, and the background which resembles most the WIMPs is a neutron recoil, which will interact with the nucleus, and this interaction is the same recoil, gives the same recoils as the WIMPs. So we need to make sure that our detector is free of neutrons at the final selection still. So this is the pulse shape discrimination I was talking about, and it's a very powerful tool to discriminate electron recoils from nuclear recoils. The idea here is that you will have, when you have the interaction, you will form argon excimers, mainly a molecule of argon, and it will decay in two states. So this comes only from the prompt light from the S1 signal, and so you have a short decay and a more long decay. And it happens that the nuclear recoil has much more of the singlet decay time than the electron, so you end up with the fraction of light that's promptly detected, that is within 90 nanoseconds of your detection, is very different for nuclear and electron recoils. So this F90 corresponds to this parameter, which is the light that's collected within the first 90 nanoseconds, and you can see a clear distinction. So we can use this to distinguish nuclear recoil from electron recoils, and this is very powerful for liquid argon, so that's why it's a good target for dark matter detections. Then we have also some vetoes. So this detector in the very inside here is the TPC, and it's surrounded by two vetoes. One that's filled with liquid scintillator, that's this cylinder here, and the outside you have a water Cherenkov detector with PMTs on the side. So this works for shielding both for cosmic rays muons, gammas, and neutrons for the detector. So this is just to give you an idea. I won't go into the normal mass analysis, but this will give you an idea. This is our data for the 530 days, and after some very basic cuts. So after this, we do analysis for the normal WIMP mass. I'll talk about this, right? And at this region here, where you have the S1 signal, the prompt signal, versus this F90, which is the pulse shape discrimination, you can see this region here is where we expect to have WIMPs. We did a blind analysis, and when we unblinded it, there were no events there, and with this we can put a limit, which just came out. And dark side is still a very small detector compared to Xenon and Lux and others, but it has, it showed that the technique works. And then if you get the normal WIMP, the idea, the models, the first expected was that the WIMP, which is a massive particle, would be above 10 GeV. So since we are covering already a big chunk of the parameter space, there's a lot of activities, both in theory and in the experimental side, to go below this value, to start to search WIMP masses that's below 10 GeV. So we did an analysis in dark side, and I'm happy to say most of the analysis was done in São Paulo, and to look into this low region. So one of the motivations came from asymmetric dark matter, where you have that the ratio of the dark matter density over the baryon density is about 5. And when you look into this number here from the WIMP, normal standard WIMP scenarios, this fact is not taken into account. It's just seen as a mere coincidence. However, there's a lot of theoretical models that shows that if you get into asymmetric dark matter, where the mass of the anti-dark matter particle is not the same as the dark matter particle, you have a connection between that leads to this number here. And for this, most of the dark matter particles will fall, the mass will fall between 1 and 10 GeV. So with this in mind, we looked into if it would be possible to use the dark side detector, which was optimized to measure above 10 GeV. So we did an analysis that we proved that it is possible for dark side to measure and to probe models below 10 GeV. So for this, we mainly used only the S2 ionization signal, We did not use the S1, and that's because at these masses, the scintillator and the prompt light is too low to be detectable, so we have to give up the pulse shape discrimination. So using this, we had two more caveats in the analysis that were very interesting. So first of all, we could measure the photoelectron yield from a single electron. And for that, what we used was a short period of a time where the getter in the detector was turned off. The getter is a device that will purify the liquid argon, so it's always working. However, there was a short period where the getter had to be maintained, and it was off. And what we see is that the number of single electrons went up during this period. So here we have the number of electrons that are extracted versus it's the number of electron distributions. And here's the data with the getter off and on, and here's the data with the getter off. And you can see that it increases. And in our Monte Carlo, we can simulate what would be the signal of one electron or two electrons, and they match very well. So with this, we have the photoelectron yield per extracted electron, which was approximately 23. So this was one of the important steps. Then the other steps brought from the fact that, so here what we are going to do is the direct energy calibration as a function of number of electrons. So this we profited from the fact that when we transported the underground argon that fills the detector from Fermilab to Italy, and also in the refining, you had a contamination of argon-37. So this here is the data in number of electrons detected. For in black, you have the first 100 days. Argon-37 will naturally decay, so then it will disappear from your underground argon. And in blue, you have the data for the last 500 days. So you can see these two peaks here that corresponds to the argon-37 will capture an electron and later on release. And these are the two different shells that this process happens, and they fall into these energies with the exact, at the exact place where it expected, both from modelings as from some measurements that were done before. So with this, we can calibrate the number of electrons versus energy. So the next step would be to understand the ionization yield from nuclear recoil. So this is very important, and that's where the uncertainty of our measurements is larger. So this, we calibrated the detector with two sources, amerilion carbon source and amerilion beryllium sources. Both of these also produce gamma, so we need to take this into account. But here's the data, so with the MB source, and here's with the MC. So in black here we have the data, and we calibrate, we try to understand the signal also with our Monte Carlo, with this it's a giant-based G4DS, and the G4DS used this model, the Bezrukov model, which includes ionization, recombination of electrons, and so on. And so with this, we can understand the ionization yield from nuclear recoils. And this is what we get. So here's the ionization yield. So it's, how mainly the number of electrons per keV extracted. This is reduced energy, which is mainly proportional. It's an eight-dimensional constant that's proportional to the energy and depends on the target atom. So in red here is what we get from our calibration with MB, MC, and the simulation with this model, and we get our red curve. And these are data points that comes from other experiments. So These two experiments here are the Aries and Scene, which were dedicated experiments to try to understand the nuclear recoil in argon. And our result is a bit lower than these experiments. So we take this difference as a systematic effect and include it as a systematic error. Anyhow, the fact that it's lower means that our limits will be more conservative. So with this, we can compare our data to what's expected from WIMP models. This is a very busy plot, but what I want you to pay attention, so here is the number of electrons detected. This is the energy in keV from nuclear recoils. And here is our data. At the end here, there's some data that there's some impurity, so we measure our signal from 4 electrons up, and we compare what we get here with these solid curves, which are what expected from certain models. So here we give example of 3 models with 3 different masses, and for a cross-section that's 10 to the minus 40. So we compare our data with these results, and this is what we get, where so here's the mass of the WIMP, the cross-section, and here is our limit. So this part here has an uncertainty because, as we've seen, the ionization signal at the lower side has some uncertainties, and we take 2 approaches here, one more conservative, and so 2 extreme approaches. One, we take a binomial analysis of the fluctuations, and the other we say that there's no fluctuations in the ionization yield. So our results would be anything between these 2 lines, and although dark side is a very small detector compared to the others, we reached the best limit for this mass region, and I think mainly because we could do an analysis that really profit from some interesting points like the getter one was off and so on. So this was a very nice result, and I will go over the second lower mass analysis was a SubGeV search, and this was motivated by the fact that you have now one of the possibilities for dark matter, it's a whole dark sector where you not only the dark matter but other particles would be in this dark sector, and you would have portals connecting these with the standard model particles. So the kind of analysis is exactly the same. It's only S2 analysis as well. And in terms of modeling, the interesting thing here is that the dark matter will interact with the electron. So it would be a dark matter electron scattering. So we looked into this, and then you have that the dark matter electron interaction will be parameterized by a form factor from the dark matter particle with 2 limiting values, a heavy and a light mediator. So we do the same kind of analysis, but now we will compare with, so the cross-section here will be different, and we compare it to different models, which includes these facts here. This model comes from these authors here, and here doing this analysis, which is mainly the same one, but comparing to different models, these are the results for heavy and light mediator. And for heavy mediator, we have the best limit in this region here. And the other results is from XENONT 100 and XENONT 10, which was done by these authors here. So we also have a nice result. And most important of all, we proved that dark side and liquid argon program can test and probe the small mass region for dark matter, and that's very exciting because we are going to a much larger detector now, and we aim to keep looking into be able to measure the dark matter, probe dark matter at these lower regions. Thank you. just in time.
Thank you very much. Let's open for questions.
Hi, hello. So I have a question. Do you hear me? Yes. I have a question about, okay, first if you can go back one slide on the yes, this one. So do I understand correctly that with this analysis you put the threshold at 3
3 electrons.
Okay, so my question is, so again, also, so in the other, let's say, low energy, low dark matter mass analysis, WIP-like, you choose to put the threshold where, let's say, the Monte Carlo doesn't stop to agree with your data. Here, you put it
here you have
below. The question is, how do you choose the threshold?
The difference here is that now we have here, it's a dark matter electron scattering. So we are not looking into the nuclear recoil anymore. And the nuclear recoil was the problem, and that the uncertainty there. So that's the main difference.
Okay, but still also here, if I understand correctly, in the region between 3 and what about 9 for the electron, your data do not really agree with the
Let me go back and...
While on the other analysis, you cut it before. Yeah.
So here you can see the number of electrons.
Yeah. So here you put the cut at 7, which is where the data and the
No, we don't cut at 7. We cut here at 4. Let me get this right. So at 7, we completely understand the background. So, and before we have some uncertainty due to the nuclear quenching. So the nuclear quenching is the main source of uncertainties here. Okay, and that's why we have this split here, because we approach the uncertainty on the quenching in 2 different ways. For the electron, we don't have this, but we have this peak here that we don't understand. So we cut it to avoid the peak at a very low region, which we don't still. We have some hints of what it is, like probably it is capture of electrons and some impurities too. But so that's why we cut it in 3 here.
Okay, thank you.
Okay, I think we could very short question and very short
okay,
answer.
I can also answer questions and the coffee break if people have more, but...
What do you think? Short question and short answer.
Yeah, I wanted to ask 2 questions, so I guess I'll ask one. I mean, I wanted to ask about that, but I'll ask you about that in the coffee. But just the other point then, so for the nuclear recoil limit, if I understand correctly, so all of your spectrum lies below the region that you've calibrated, right? So you've calibrated up to like, what was it, 10 keV in QI? Was that correct? You've got the QI plot.
Here you mean?
Yeah, okay, so it's like 7 or 8 keV in the... Yeah.
Yes, so here you have...
No, that's the other plot I was thinking about. So the other plot shows you your calibration data in the QI, right?
Slide 17.
Yeah.
Okay.
So this is your calibration data for nuclear recoils, yeah?
Yes.
But all of your signal, dark matter signal, lies below like 7 keV. And so you're just using all of this extrapolation.
Well,
so I guess
7 keV is here. This is data from other experiments, right?
Sure.
So.
But are you not saying this is your nuclear recoil model? This red line?
The red line, yes. So the red line is the recoil model, but it comes lower than 7.
No, I see that, but do you worry that, I mean, I would like to see calibration data there to actually trust have full confidence in your limit. So my question is, are there plans to get calibration data below the 7?
Oh, yes. So there's an effort to be doing this, and there's an experiment called RED, where we're trying to understand it's better to make sure that with the larger detector.
Okay. Thank you very much. Ivone? Hi. Fabio will take care of the microphone. To change the slides, you have this device where this is the pointer, this goes on, and this goes back, and that's
Let me try.
Yeah, you can try.
Okay.
Okay, so you are all set.
I'm set.
Our next speaker is Adam Brown from the University of Zurich, and he will tell us the news about xenon detector.
Okay, thank you. So my job's made really easy now because the first part of my talk you already heard. You just need to replace Argon with xenon. So just to give some... yeah. Okay. So just to give some context, you can still hear me? Yeah. To give some context, I'm going to talk today about xenon 1 ton mainly. So this is the current iteration in a series of 4 experiments, starting, well, 10 years ago with xenon 10, and increasing. So every time we've almost multiplied by 10 the size of our detector. So xenon 1 ton was taking data since 2016, and we published some results this year to talk about today. And now there's a lot of effort going into xenon n-ton, which is the next generation of the xenon experiment that we'll be commissioning starting next year. And of course, something like xenon is not just the work of me alone. So xenon collaboration now across 3 continents. So we have some Japanese collaborators, and it's 160 scientists, last count. Okay, so here's a picture of xenon 1 ton. So xenon 1 ton is in the Gran Sasso laboratory in Italy. If you get bored later, you can go on a tour of LNGS, which is on Google Street View, actually. So you can follow the link here. Unfortunately, they're 4 years old now, and xenon 1 ton was still being built, but you can see the scaffolding at least. So here on the left, you see this huge water tank, and on the water tank is... Does that work? Yeah.
This should be okay. We have very little experience with
Okay.
monsters, so I think it should be okay.
Okay, I try not to shake my head.
It's more like in which direction you talk.
Okay, so on the outside is a photo of what's inside then the water tank, and right at the center here you see the volume, the cryostat, that's where the real detector is. And everything else around is because you don't really build dark matter detectors, we build particle detectors. This will detect anything that goes in. And so outside we have this huge water tank, and this is a muon veto, and I talk about why we need it later. And then on the right-hand side is the service building, so this is where all the hardware needed to run such an experiment is. So at the top is where we purify, where we do have all the cryogenics for the xenon, data acquisition in the middle, and then at the bottom this krypton distillation column. Again, I talk in a bit. Okay, so how does this technology work, this dual-phase TPC that we have in xenon? You heard already in the previous talk about liquid argon TPC, which is the same operation principle. The main difference that we have is that we cannot use pulse shape discrimination. So in xenon, the longer lived, we still have these triplets and singlet states, but they both have very, very short half-lives, and there's no way that we can use pulse shape discrimination. So instead, to discriminate, is it working? To discriminate, okay. Yeah. To discriminate electron and nuclear recoils, we use the fact that the S2 signal, the S2 to S1 ratio, or the charge to light ratio, is different between an electron and a nuclear recoil. So in an electron recoil, which makes up the bulk of our background, we see a lot more charge and a lot less light than a nuclear recoil. We get somewhat worse discrimination, unfortunately, than the liquid argon experiments, but there are other compelling reasons to use liquid xenon that make it worth it for us. So everything else you already heard, we get this S1 light signal immediately when the particle interaction interacts in the xenon, and then sometime later an S2 signal. And the S2, this light signal, which is produced at the top after the charges drift up, is very localized on our top PMT array, is how we get position reconstruction. So here's some photos of xenon 1 ton itself, the same sort of thing you saw for dark side on the outside. And this is our photomultiplier tubes from the inside. So it's a much bigger version of dark side. We have 127 of these PMTs on the bottom and 121 on the top. And if you just look, so on the left here, you see this idea of our TPC. So basically, we have at the top and bottom these photomultiplier tubes to collect the light signals, and everything around the outside is covered in PTFE, which reflects the xenon scintillation light very well. Okay, now I'll talk for a few slides about how we calibrate the detector, how we know what we are seeing. So to do this, we have such a huge detector that if we put a radioactive source outside, then in our sensitive region that we actually search for dark matter, we won't see anything. So the shields everything from outside, and we can't use a radioactive outside. So our two main calibration sources we inject. One of them is krypton 83M, so this is a stable state of krypton 83. So we inject this into the liquid xenon volume. It's not bothering me if it's working. Okay. Okay. So we inject this inside the liquid xenon, and krypton 83 has this nice two-stage decay. So it has first of all a 32 keV decay and then a 9 keV decay, and they're very shortly after each other. So if we look for events where we have two decays in a very short time, we can be fairly sure that it's krypton 83M. And so we get a very clean sample of these events. And both of them are monoenergetic, so we know exactly how much light we should be seeing, how much charge we should be seeing. And we use this to calibrate differences in the efficiency to collect light across the detector. So depending on where a particle interacts in our detector, maybe you see more light, less light. It's mainly geometrical effects. And the same for the charge yield. So at the top, when we produce this secondary scintillation light, depending on the electric field, if the electric field is a bit higher, maybe we see a bit more. If it's lower, we see a bit less. And both of these effects we can calibrate very accurately using this monoenergetic decay that we can really very carefully select. And the other thing that we do is we have sometimes some field non-uniformity. So the electric field is obviously not perfectly straight. It's very difficult to build a very high, perfectly straight field. And so then if you have an event that's at the bottom and the outside of the detector, it tends to drift in as it moves up. The electrons tend to drift in towards the center. And we can correct this effect because we know that we should be seeing a perfectly cylindrically, uniformly distributed set of events from our krypton 83M source. Okay. So then we have our response in light and charge calibrated. Now we need to know how we can distinguish between electron recoils, our main background, and nuclear recoils. And for this, we use to calibrate the electron recoils, another injected source, and this is radon 220. So this we again inject, and it decays in about a minute or so. It goes through this two-stage alpha decay that's not interesting for us, but then it decays into this lead-212 isotope that has a half-life of 10 hours and gives us a beta spectrum at low energy. So we get lots of beta events throughout our detector, and this models exactly our background of beta events. And so you see here in the middle the plot of on the x-axis the light, the S1, on the y-axis the S2. So this type of plot you'll see a lot, and in blue is the events from our radon 220 calibration data. So you see that there's quite a well-defined relationship between the light and the charge signal for a given energy. And of course, as I move up towards the top right of this plot, I'm looking at higher energy events. And then for the nuclear recoils, so for this we do have an external source. So we have a neutron generator that we lower down into the water tank outside the cryostat. So if anyone has an idea for an injectable source of neutrons, then we'd be very interested. But at the moment, we're stuck with an external neutron generator. And again, we do the same thing. So you see, this one. So you see, again, in the red events is events from the neutron generator, so neutrons. And we have another well-defined relationship, but with a different S2 to S1 ratio. And both of the shapes of these bands parameterize using a physical model. So we model the microphysics in liquid xenon. So actually, it's not such a simple process, the way that you get these ionization and scintillation signals. And we model this using a physical model and fit it to the calibration data we see. And that's what you have here. So you have the light yield on the left and the charge yield on the right for both electron and nuclear recoils. Okay, so now basically the whole game of searching for dark matter is to understand what backgrounds we have and how we can avoid them. So here I talk about the electronic recoil backgrounds, which makes up the vast majority of the event rate Although, as I said, we are able to distinguish them from nuclear recoils where we expect the signal by the S2 to S1 ratio. So we have just a minority contribution from the materials in the Teflon, the copper, the stainless steel in our detector. This we basically get around by looking only for the analysis in the central part of our detector. So all these events from the materials tend to be at the outside, and we don't use this region for analysis. Then there's a very small contribution again from solar neutrinos that scatter off electrons. And then the bulk of our backgrounds are actually intrinsic in the liquid xenon. So one of them is krypton 85. This is created basically from nuclear weapon testing, and but this we remove from the xenon before we fill it into the detector. So because it's completely anthropogenic, it doesn't keep entering the xenon. We distill the xenon before we fill it into the detector, and we can reduce this easily to a subdominant level. And the main background for us is radon 222. So this is emanated from materials inside the detector, inside cooling plants, everywhere particularly in the steel. And it's constantly entering, and it has a half-life of about 4 days. And so this makes up 85% of our backgrounds. And really the only way at the moment that we can control this is to try and select backgrounds with a low emanation rate of this radon, and to avoid having them close to where the xenon enters the detector. Maybe one interesting background in the future is xenon 136. Now, this is the only long-lived unstable isotope of xenon, and it goes a double beta decay. And so at the moment, this is a background for us. In the future, maybe it's an interesting search for physics of neutrinoless double beta decay, which maybe Janina will talk more about in the next talk. Okay, now maybe the more dangerous backgrounds for us are the nuclear recoil backgrounds. So these can mimic really a WIMP signal detector, and this basically means neutrons at the moment. So there's a very small contribution at the moment from coherent elastic neutrino nuclear scattering. At the moment, we expect fractions of events per year. So this is the all-in events per 1 ton year, which our analysis was done in. And also cosmogenic neutrons. So this is why we have the muon veto. You can have a neutron created by a cosmic muon that goes through, for example, the water tank or the detector materials. And if this produces a neutron in your liquid xenon, then you can think that this might be a WIMP. And the muon veto, we have to avoid this sort of event. So if we see a muon that goes through the muon veto, which is just a Cherenkov muon detector, this huge 10-meter water tank, then we don't look at any events that happened in coincidence with it. And here we have 99.5% or so efficiency to tag these events. So then our real background comes from radiogenic neutrons, from the detector materials, so from alpha N, for example. And here again, this is in 1 ton core volume of xenon 1 ton. We expect about 0.6 or 1 event per year. And this is something that's difficult to reduce. Again, we can only select materials that tend not to produce these radiogenic neutrons so much, so we have careful screening of the materials. But also, if we choose carefully our fiducial volume, we can reduce the rate. So this plot again I have a bit later, but in the very center of the detector, we have much lower rate of these radiogenically produced neutrons. They tend to be really concentrated around the outside of the detector near the materials. And then maybe a couple of other backgrounds that we have that are not so much physical backgrounds. So one of them is accidental coincidence. So all the time, anyone who's worked with PMTs knows that you have a fairly high dot count rate. So we get effectively single photon light signals all the time. And if these combine with an electron that appears from somewhere, or a couple of electrons that appear from somewhere, maybe it's got stuck on something inside the detector, then we get a signal that can look something like a real event. Yeah. And this we just model very easily by taking single S1, single S2s. We know how much we expect. And then something that became important for us in our latest analysis were these surface events, so events that happen right next to the wall. And because at the wall we can only detect the position of the events using the PMTs at the top, and at the wall only half of the S2 is seen directly by the the PMTs, and half of it's coming reflected from the wall. This is where the position reconstruction is most difficult. And so these events can actually be reconstructed a lot further in from the wall. And they also can lose some of their charge on the wall. So some of the electrons that are released that form the S2 can be trapped on the Teflon in the wall of our detector. And so then this reduces the charge to light ratio. It can make them actually look more like a nuclear recoil. Okay, so now I'll show our search result data. So here is in the light and charge space, S1, S2. Every point here is an event that we saw in our year-long data run. And every point here is a pie chart. And the pie chart shows in the best fit, what proportion of the PDF for this event came from ER, from surface events, from neutron, and so on. So all of our backgrounds that we identified. So most of them are dominated completely by one event, but really every point is a pie chart. And the biggest points are those that have a significant WIMP-like contribution in the best fit. So you see here again the same electron recoil band, and below it in purple is the expected signal for a 200 GeV WIMP. And then down here, this blue is what I was talking about, the surface events. So you see again on the right, it gives a function of radius, and the surface events are concentrated near the wall. And we analyze this data then with an unbinned profile likelihood with 3 dimensions unbinned, which is this S1, S2, and radius. So everything is a function of S1, S2, and radius. And finally, we have a 4th binary binned dimension, which is whether the event came in this core volume here that you see in green, which we identified as being much freer from radiogenic neutrons. So here again, this is our dark matter search data, just plotted in position instead of in light and charge. And after we run this data through our likelihood, then you see here the results. So here's our exclusion limit from 1 ton near of data. So the sensitivity was 7 times better than previous generation experiments. You could say that we were a bit unlucky for most high mass WIMPs, or maybe we were lucky to see the first hints. But the limit is up by about 1.5 sigma compared to our sensitivity for high mass WIMPs and slight underfluctuation at low mass WIMPs. And okay, you can read the minimum of the slide. Okay, so in the last couple of minutes I want to talk briefly about the work that's going on now towards Xenon N-ton. So what we hope to finish by next year to start commissioning. So obviously I mentioned at the start that the main difference is that there's a much larger TPC and the bigger xenon volume. So we're going from a total of 3.2 tons of xenon in liquid xenon in Xenon 1 ton to 8.4 tons in Xenon N-ton. And this will allow us to make the fiducial volume used for analysis maybe 3-4 times bigger than we had now. But apart from this, we also have a lot of work going on to reduce the background rate in the detector. So one thing is making it bigger, the other is making the background rate lower. And so I selected 3 of the things that we're doing to put on here. One of them is liquid xenon purification. So at the moment, all of our purification, removing electronegative impurities, happens in the gas phase. And this is very slow, to have to evaporate all the xenon and then to condense it again and only be able to purify in the gas phase. So for Xenon N-ton, we're going to start purifying in the liquid phase in cryogenic. And this will allow us to really massively improve the rate we flow through the purification system compared to the current system. Another is radon distillation. So at the moment, we distill, like I said, we distill krypton from the xenon just before we put it into the detector. But what we're going to do now, and we already started to work to test this in Xenon 1 ton, is online radon distillation. So continuously operating while Xenon N-ton is running, we'll be distilling the xenon through this distillation column and removing radon from the xenon. The nice thing about radon is because the half-life is only 4 days, we can then, once we collect the xenon and let the radon decay, we can put it back inside the detector after 4 days. And as I said, this is something that we tried this with the krypton distillation column of Xenon 1 ton, actually, so we just reversed the column and ran it in reverse. We can't recycle the xenon if we use the current column. But we saw already a 20% reduction in the radon rate just using the krypton distillation column in reverse. And finally, a big change that we'll have is the neutron veto. So now that the neutrons are becoming a really important background for us, we're going to dope the water in our muon veto tank with gadolinium to be able to capture neutrons on it, and then just optically separate the inner part of the water tank. So we'll have some optical screening on the inner part and more PMTs around just around the inner part of the water tank to detect the scintillation light that we get then when a neutron gets captured on the gadolinium. And this will give us maybe 90% or so ability to veto neutron events that happen inside the TPC. And so I think I came to the end of my time just perfectly. So I said everything. So, and as I said, Xenon Enton, now we're looking at commissioning next year, starting in the middle of next year. So thank you.
Thank you very much for the talk and for staying on time. Now we have a few minutes for questions.
One, maybe two questions, depending if I have time. The first one, very simple and easy. Maybe you know better than me. It's newer news. Can you still put the gadolinium in the water tank at Gran Sasso? Because I knew that there were some issues about security, environment. The NFM president and the director are under judgment. So
we think that we can put the gadolinium in, and it is not a problem. And one of the nice things about gadolinium is that we're able to start running without the gadolinium in the water tank. So compared to using a liquid scintillator or something, it's just something that we can put into the water afterwards without taking it out. So then this takes some of the time pressure off getting approval.
So it's not a
but it should not be a problem. We don't see it being an issue to get approval to put the gadolinium in.
So from the environmental point.
From the exactly.
Okay, thank you. And yes.
So maybe you say that, but the last part of Xenon Anton was a bit fast. If I look at the plot, is it right that you're going to hit the neutrino floor and you will see something?
So in the low mass region here.
In the low mass region.
Yes.
Do you expect to see actually?
We expect to get some events. And we have an expected event rate that's like order events. It doesn't mean that we'll have statistics to necessarily see something. It depends also whether we're lucky or not.
Yeah. I have a question about your signal model.
Yes.
Can you go back to where you show it again with the calibration data? Sorry for asking.
Just
keep going back. It's your QI, LY stuff.
This one.
Yeah, exactly. So I mean, you have a data point up. If I look at the top right plot, do you have this data point that you just don't go through? Is that why do you not care about that low energy data point in the charge yield of the electron?
Up here. This red point up here you're talking about. This is not ours.
I know, it's Lux's. But because you don't go through it, it means you have an enhanced light yield. So if you look at the other plot on the left, your light yield's a little bit enhanced. I just wonder if... So you just don't fit to other collaborations' data? Is that
so we do use them as a prior in the fitting. And then we let then some of the parameters go into our profile likelihood, the most important parameters. So I think we have two selected parameters which are not actually physical parameters that go forward into the profile likelihood.
Okay, I think we can thank our speaker again. And our next speaker is Janina Biondi, correct? So Fabio will take care of the audio and I will go to the presentation.
keep static. Okay. So this is, yeah. Okay.
Okay, so next talk is about DARWIN, the ultimate dark matter detector.
Okay, so thank you. Here in my talk, I'm Janina Biondi. I joined the Darwin collaboration this year for my PhD. What's DARWIN then is just another unnecessary acronym for a dark detector that is part of the XENONT family. So this is the scenario right now. These are all the dark matter exclusion limits that we have around, more or less. We have here all the noble liquid experiments that set competitive limits, like dark side, like LUX, like xenon. This is the projected exclusion limit for xenon and TAN and LC. And DARWIN is the next step from xenon and TAN, and the aim here is to explore the entire parameter space until we reach the neutrino floor that is our irreducible background. So, as didn't mention, this is the spin-independent cross-section. But because we are using xenon, we are also able to set limits in the spin-dependent cross-section, since xenon has stable isotopes that have a non-zero total angular moment. This is not the case for argon. This is one of the good reasons to use xenon. And yes, this is the evolution. We started with xenon 10. In 2008, with 10 kilograms, xenon 100 in 2012 with 100 kilograms in the active target, xenon 110 that has approximately 2 tons on the target, and the next step will be xenon and TAN that will have approximately this as an active target. In 2019, that is next year, it will be commissioned. And for 2025, what we will have is DARWIN, that they will count with 40 tons of liquid xenon as an active target. So this is the baseline design for DARWIN. It will be as well a dual-phase time projection chamber. It will count with 50 tons of liquid xenon, 40 in the active target. And the dimensions of the TPC will be 2.6 meters diameter and 2.6 height. It will come with 2 arrays of photosensors on the top and on the bottom. And we are considering here if we keep the PMTs that we use and work well for xenon 100 at 1 ton, or we change to something like silicon PMs that have a lower background, and those are part of our R&D right now. So it will come with a drift field, the same as a xenon 1 ton. This is a challenge because we need to deliver a high voltage that, as we know, LUX wasn't able to reach, and xenon 1 ton was expected to have a higher voltage. So this is also part of our R&D. We will come with this low background double cryostat, as well as our PTFE reflector panels like xenon 1 ton, our auto sheet field water Cherenkov. And we are considering here either having a neutron beton scintillator or a gadolinium doped water tank gas, like xenon and ton is supposed to have. So the dimensions for the water tank will be 14 meters tall and 14 meters diameter. So this is the baseline design. There is a double-phase TPC. We have here the high voltage delivering, the top photosensor array, the PTFE reflector to maximize the charge, the light collection, the double cryostat, and as well the usual electric field that we use to extract our electrons. Well, You can do it manually.
Maybe it's disenchanted now?
Yeah, I think okay, sorry.
Okay, it's okay. So right now we are incorporating this baseline design in simulations. This is my work. I'm working right now with simulations. And because we need an estimation of how much background we are going to introduce in our detector. As I said, it will be a huge detector compared with the ones we have right now. So I will not take much time in describing how a dual-phase TPC works because it was described before. No, it's not working. The pointer. Okay. So we have our interaction here. We have that it gives us this prompt scintillation signal. Free electrons that are drift to the gas phase where they produce this ionization signal. And because of the charge density, the position is different for nuclear recoils and electron recoils. Our signals are expected to be different. And this is what Adam described to be or discrimination in xenon experiments. So we have the electron recoil events, the nuclear recoil events. In the nuclear recoil events, as I said, is the scattering of a xenon nucleus, and the electronic recoil is the scattering of electrons. And this is how we perform our discrimination with the ratio of our two signals. So for electronic recoils, what we will have is the extrinsic contamination background from the materials, as well as the intrinsic background from in the liquid xenon. And we will also see the solar neutrinos if we aim to see to explore the entire space. So as we can see here, this is the estimated evolution in the background compared with the fiducial mass. And Darwin will reduce one magnitude order the expected background for xenon and ton. For the nuclear recoil part, we will have the neutrons from materials as well, the homogenic activation, and now this will become an important channel, the coherent neutrino nucleus scattering that will come from the neutrinos in the sun. So, given its projected log background and sensitivity, Darwin will not only be an observatory for dark matter, we expect to see other channels as well, like solar actions and action-like particles, low energy solar neutrinos, but the neutrinoless double beta decay if the neutrino is a Majorana particle, a coherent neutrino nucleus scattering. We can study this process that was observed by Coherent last year. And supernova neutrinos, this is also a very interesting channel. For solar actions and action-like particles, this will produce an electronic recoil signal. And galactic actions and action-like particles are well-motivated dark matter candidates, so we can explore also other candidates besides WIMPs. These solar actions are produced via Bremsstrahlung, Compton, etc. And this is the projected sensitivity compared with Xenon 100 and the device. So, low-energy neutrinos will be possible background for Darwin, but they will also give us the possibility to study this process, not only as trying to filter it as a background. So, the PP neutrinos and the 7 beryllium neutrinos are more than the 98% of the total neutrino flux. So this is an important channel. And not only we will have the opportunity to describe the properties of neutrinos, we will also can infer some properties about the sun with this, since these are the main mechanism of the sun. This is a comparison with Baracchini, so we are hoping to access this region here. This is a rough estimation that we will observe 2,000 neutrino events per year The error precision below 1% can be reached after 5 years of data taking. So this is more what I'm doing right now, is the studying the neutrino less double beta decay. As I said, if the neutrino is a Majorana particle, we expect to okay. Given that we have 136 xenon that has a natural abundance of 8.9% xenon. Without depletion in our xenon, we already have this abundance here. And the Q value of this is 2.458 MeV. That is well above the energy range of our expected WIMP signal. So this is the expected region that we want to cover, and Darwin ultimate means that if we can reduce our backgrounds and have a 10-year exposition, we can also access this part in which we can explore the normal hierarchy. Yes. So without isotopic enrichment, Darwin's target contains more than 3.5 tons of 136. So the challenge here, I didn't mention it, but it will to develop our detectors that can have a good response in a few keV signal, region signal for our WIMP searches, and also a high energy good response. So right now we are studying with the current geometry how it will be our sensitivity, but the projected sensitivity is 2 orders of magnitude improvement compared with xenon 1 ton. Here we can see xenon 1 ton, xenon n ton, and finally here Darwin with 6 tons of initial volume. Why 6 tons is that for double neutrino-less double beta decay, you don't win that much by fiducialization, given that you are studying this high energy region. It's not like WIMPs that we study the low energy region in which by having our shield made from xenon, we gain a lot in sensitivity. So another interesting channel is that Estrigari said, I'm quoting here, is the rate of low energy signals in a multi-ton WIMP detector will eventually be dominated by interactions of cosmic neutrinos via coherent neutrino-neutrons. This will come mostly from A2B solar neutrinos, which produce nuclear recoils that are below 3 keV. Darwin will be able to detect and study this process. Not only that, Darwin will be sensitive to all extraneous species via neutral current interactions, including neutrinos and antineutrinos that are emitted by core collapse of supernova. And this is here, published in 2016, or expected detection significance. This is like a... So what signals do we expect to see in each region? We have here the WIMP region, we have here the electronic recoil region, and it's not plotted here, but we will also have our coherent neutrino nucleus scattering that are low energy events in the WIMP region as well. So right now we are here. We already got 2 groups got funding from the ERC. Darwin is right now is 28 groups from 11 countries, and it's on the APEC roadmap, and it has a lot of synergy with Xenon N-ton R&D since we are facing the challenges here. It's expected to start running in 2025, so right now there's no detector to show. So right now we are addressing the design challenges that are related to, we will have a longer drift length. For this we'll need to deliver the necessary high voltage. we will have an increased mass. So for this, we will need to improve our cryogenics and the liquid xenon purification, as Adam already explained here. We will need to improve our detector response in calibrations, in the corrections and readout. Right now, we count with optimization of our cryostat design. Thanks for the NICE engineering group. And we will also have challenges in our backgrounds, since we will have far more material, and we know that the PTFE from our TPC has an emission in neutrons, for example, and we will have a larger cryostat, and we know that this also introduces background in our TPC. So right now, how we address this thing is that we screen our materials to get the cleanest materials that we can get, as for example, copper and stainless steel. And we have this facility in LNGS called Gator that is gamma spectroscopy. We are developing right now techniques to monitor the liquid xenon purity. We will have a purity monitor in our detector to control at all times or quality of the signal, because the liquid xenon purity affects the S2 signal that is produced in the TPC. For the cosmogenic background, we will need to decide where we place the detector, as we need to go deep enough to get rid of the muons, and right now, we are here in LNGS. This is one option, but also the size of Darwin is maybe more suitable for other places. We need to decide about this. And yeah, this is the projects that we have in Zurich. For example, we will build a TPC that will reproduce the same length as Darwin, to demonstrate that we can drift electrons into 0.6 meters, and that we can apply the necessary field to drift the electrons, and also to start testing our purity monitors and our liquid xenon purity. We will have a focus, obviously, in the cathode developing and the high voltage feed-through test. And in Freiburg, they are developing something that will have the diameter, more or less a diameter of a TPC, because we are also dealing with mechanics challenges, like the cathode can have some, the electrodes can have some deformation, as it will be a huge detector, and you can expect to have a disk without deformation, because it will deform by its own weight. So they are studying this right now in Freiburg, and we are already on the way for this. So as a summary, Darwin will be the ultimate liquid xenon for dark matter detection for WIMPs, and it will also provide a unique opportunity for the rare event searches, such as low energy solar neutrinos, neutrinoless over beta decay, coherent neutrino nucleon scattering, and actions and actionless particles. And Darwin right now is a growing collaboration. We expect to have all the experience and knowledge from the Xenon Enton group once they move to the next phase, and currently we are 28 groups from 11 countries, so thank you.
Thank you very much for your talk.
I'm sorry. So I have a question, very curious. How would you discriminate the neutrino from coherent neutrino scattering from WIMP event of 10 GeV?
This... You're talking about this one?
Yes. How can you discriminate this from a WIMP-like event?
I think at this point, we are expecting not to discriminate anymore because it will be like the 3 keV region. So
What do you mean? I mean, that kind of event would look just like a WIMP recoil of 10 GeV or 5 to 10 GeV. So how can you say you can do neutrino physics if you cannot discriminate that from WIMP? Or on the other side, how can you say you can sensitive to WIMP of 10 GeV mass if you cannot discriminate from neutrinos?
yeah, that's a good question. I'm not into the details of these solar neutrinos.
No, he's talking about the Aron baronate neutrinos, the nuclear recoil. These are what I'm talking about. Yes, I know they cannot. That's the point.
I do have a question.
Yes.
So I mean, going back to this neutrino stuff, especially the PP stuff you show, so you have to get the radon background down to do any of that stuff below even what Xenon and Ton want to do. Do people know how to do it, or is it just that you hope that someone will figure out how to do it in the future?
No, but there are already studies right now in Colombia with the liquid xenon.
I guess my question, if you already know how to do it...
distillation with the liquid phase, not only the gas phase. So with that, we can achieve a good purity on our liquid xenon.
But then why don't you do it for N-ton? Why don't you do it? So you want to go down another factor 10, you said, from N-ton to Darwin.
Yes.
So if you already know how to do it, why don't you do it for N-ton?
Because the factor, mostly because of the more xenon mass to filter, to act as a shield.
But isn't it radon is dispersed throughout the whole volume, so...
Yes, but the radon is one of the backgrounds that we can hope to reduce as its most lower level.
And you know how to do it?
Yeah, more or less.
Okay, we have time for one quick question.
Yeah.
The plot on the axion limits. I would like to ask, what is the coupling that you're probing on the vertical axis? Maybe you say that, but it was a bit fast. And what
Here?
process? Yes. And what process you're going to probe? And if I understand the black line, the dashed black line, that's a limit from astrophysics.
Mm-hmm.
And so that region seems to be already excluded, no?
The region, sorry?
So the region below the dashed black line is the one which is allowed by astrophysics. So it seems that all of these experiments are probing the region that is already excluded. Is it fair to say? Yeah, the red, the black, yes.
Yeah, but I don't get the question. Sorry.
So it seems that the region is already excluded by other experiments. I think it's an existing bound, the red giant.
Xenon 100 is the
I'm talking about the red giant line.
The red giant.
The one at the very bottom of the plot. The black dash, yes. Red giant.
Yeah.
Yeah.
It's not
Okay, no, I mean, it's an
for sure it's
independent,
not a direct observation of this.
This is okay. This is more solid.
Okay. Thank you very much again. You did great.
Thank you very much.
Sì, sure.
Allora, adesso funziona.
Ok.
Poi se dovesse smettere,
Vado
magari
avanti.
come antichi.
Sì.
Quindi questo è lo slide avanti, questo è lo slide indietro, questo è il puntatore. Ripeto, be ready for unexpected.
Ok.
Okay, so our the last speaker of this session is Elisabetta Baracchini from Gran Sasso Science Institute and INFN in Italy, and she will present us the CYGNO project for directional dark matter searches.
Okay, thank you very much for giving me the chance to present here. This is actually a new project that we are working on and a new experiment that we are trying to build at Gran Sasso. So this is a very quick outline because I will try to go very, very fast in a small introduction that is just to show you why I think, in my humble opinion, that directional dark matter search has some features that other kind of search do not possess. And in particular, I apologize for the previous question, but the neutrino is part of this actually, and I'll show you also that this is a part of an international collaboration and a vision, let's say, that is called XENONT TPC to develop a 1-ton scale directional detector scattered all over the world. I will show you which is our approach toward this vision and which is the R&D that we developed in these years that were so successful, I would say, in my opinion, that it led us in a couple of years to the XENONT experiment, concept, roadmap, and sensitivity. So again, very, very quickly, how do we do the direct dark matter search? We cannot see dark matter, so we make it bump against something that is detectable, no? Like playing with pool. And what we actually see, it's what is recoiling, okay? So challenging from this point of view is that this is a highly non-relativistic collision, and so the expected nuclear recoil energy that you're going to see is very low, and this is the reason why it's certainly not trivial to do direct dark matter searches. Above all, because we are full of backgrounds, and this is just a funny picture to show how much the banana that you hit every day has electron recoils coming from the potassium, which is of the order of 100 events per kilo per second, against what is not expected, which is actually now the xenon limit. We see it's kind of 2 orders of magnitude even lower, but we expect less than 1 event per kilo per year of dark matter. So you can understand why this is very difficult experimentally. You also have heard in the previous talk, which are that our main, let's say, background, of course, are electron recoils. These might come from different sources, and that we could try to let's say reject or protect while looking at dark matter that is like really a needle in a haystack. So you heard that okay, against the cosmic rays and cosmogenic activation you can go underground. Again, this is a picture of me in the Bulmi mine, which was very cool to see, just by the way. And you can add active and passive shielding, but at the end what you will need will be an active electron nuclear recoil rejection, which is not available to an experiment, or a different experiment have different performances. This again, you have to find the natural radioactivity, and with this you play with material selection and screening. You heard about this, but again, eventually you will need an active background discrimination, which again is not available to everybody. A very bad the background also comes from what is called radon progeny recoils, or RPRs, which is something that comes mainly from the detector surfaces. In order to reject this, you need what is we call fiducialization. You heard about this again, and this is not available to an experiment, or in some experiment is more or less efficient. So we just heard that, for example, in xenon 1 ton, they need to give up nearly half of the volume in order to reject this kind of event, okay? And finally, we have the infamous neutrino that we just talked about from sun, atmospheric, and diffuse supernovae. But among these, you really do not have any way to discriminate this kind of event against a WIMP-induced event unless you correlate this event with a source, or else if you have a directional. This can be done only for solar neutrino, because for solar neutrino we have a source, but you can understand that also for diffuse and supernova neutrino, this is much, much more difficult. Diffuse and supernova neutrino will be a background for high search masses, and solar neutrino for low masses, like below 10 GeV. So you can understand why it is very difficult to build this experiment and operate. So what we heard before, Lily, chapeau to this experiment that had managed to operate a ton scale. and we are trying just to get into the game, so we are new to this. While I'm talking about the directional dark matter, so we have talked about backgrounds, let's talk a little about signal. So the easiest thing that you usually measure is that the recoiling, the energy of this recoiling particle, okay? The point is that the energy dependence of this recoiling particle doesn't have a real peculiar feature. This is just a decreasing exponential. And you know, I mean, if you are experimentalist, you know that everything can fake a decreasing exponential, especially background, especially at low energy. And this is what most of the experiment, current experiment measure, okay? Another thing is that, why we have dark matter, why we think we can see dark matter? Because we are moving around the center of the galaxy, no? But the Earth is also moving around the sun. So for alpha here, let's say you sum the velocity of the Earth with respect to the motion of the sun, and for the other half of the year you subtract this. What this induces? This induces a temporal dependence, which is a few % annual modulation, which is actually what the Dama claims come for, okay? While you have an even more clear signature, that is, since we are going around the center of the galaxy, rotating, whatever, that you expect the WIMP to apparently come from the Cygnus constellation, because we are moving toward the Cygnus constellation in our rotation around the center of the galaxy. So this is a directional dependence, and it's a correlation with an astrophysical source that no background whatsoever can mimic, and it will induce an order 100 forward-backward asymmetry in your signal. So this is a very, very strong signature of a dark matter event. What's the problem is that, of course, this is, let's say, you can take an increasing reliability of the observed events, but at the same time an increasing difficulty in the experimental technique. And so this is why doesn't exist yet this kind of experiment, or they're still at the R&D stages. What you can do with a directional experiment. So I try to convince you that you have a better capability to reject backgrounds, because any kind of backgrounds will be isotropic, especially neutrons. Neutrinos will be from the sun. And in principle, there are studies that you can be sure, let's say, to have detected a 5 sigma level, a WIMP signal, just with an events. The other thing is that since you can correlate the direction of the observed event with an astrophysical source, you can correlate neutrinos to the sun, so you can do really neutrino physics, because you can discriminate an event coming from the neutrino from the sun from a WIMP-like event. Also because Cygnus and the sun never superimpose during the year in the yearly rotation. So Cygnus and the sun are never in the same position, okay? What is even better is that once you have a very big detector and a lot of event, you can actually determine the dark matter property, both in astronomy, meaning the velocity distribution, the density, whatever, and you can also determine the dark matter interaction in terms of coupling. This is just an example. You can look it up, and there are a lot of this study, okay? So the Cygnus TPC international project has this vision of building a galactic nuclear recoil observatory. So our idea will be a set of type projection chamber, gaseous this time, not liquid, which will be scattered, let's say, all over the world, so that the sum of all of them gets to the ton scale. We want to have an efficient electron-neutron discrimination below 10 keV of recoils in order to explore the low mass region also with different and multiple targets. We will be able to really do boron 8 solar neutrino studies with coherent scattering, because we will be able to discriminate them, and eventually we want to test the WIMP hypothesis below the neutrino floor, which to all other experiments it's something that cannot be let's say broken, okay? So this is an example of the idea that we have. The other are still idea around the world. We are a collaboration between UK, USA, Japan, Australia, and Italy. And what I will be showing you is this CYGNO, which is one of the first, let's say, module that will be built in this collaboration. Okay. Of course, we want to achieve, let's say, zero neutron background, full fiducialization in all the direction, and I said the gamma discrimination, and of course, all of this with directional sensitivity. So the approach that we chose, as I said, is a gaseous type projection chamber. You heard about the liquid. this is even more simple because you have the track ionizing your gas. You have this ionization that is drifted by an electric field to your amplification plane and read out. You amplify the signal and you read it out. So we use a micro-pattern gas detector, which are kind of new amplification devices, and in particular we use GEM, and we use an optical readout, be PMTs and scientific CMOS camera. The CMOS camera are the one that you have in your cell phone, okay? So we add that optical 3D readout that I will show you. Why? And the other choice is this. You can see this is not a, let's say, reconstruction artistic. This is how we see our event in our detector. So you can see how much a neutron recoil looks different through an electron recoil of the same energy. And the other, let's say, innovation is the use of helium with CF4. So the helium, being so light, has a very good match, kinematic match to low mass WIMP. So will allow you to explore the low mass region better, let's say, than xenon or other heavy target, and at the same time we will have fluorine, which is spin odd, so we will have at the same time sensitivity to both spin dependent and spin independent coupling. So how do we achieve this three-dimensional optical readout? We have on one side this, so we have, as I told you, we have the ionization. In the amplification of this ionization, which is charge, okay, the electrons, actually also photons are produced together with this. And then we look at these photons. On one side with this, as I told you, these are cameras from the cell phone, and this is how soft electron or recoil looks in this kind of camera. They are market pulled, so they are developed independently from the scientific, let's say, field. They are decoupled from the target, so differently from xenon or DARWIN or the other experiment, which have the detector inside, looking at the target. These are far away, and they're very well matched to the CF4 spectrum. So you have a bidimensional projection of your track like this. With the PMT, you can understand from the shape of the signal in your PMT, let's say, the direction of your track with respect to your drift direction. Combining these two, you can achieve three-dimensional tracking, which we demonstrated in this paper, with order 100 microns position precision. So again, these are just a couple of pictures to show you which are the potentialities of the device. You can see how much different they look, these kind of tracks. And this is a very familiar picture, which is also the start of my talk, showing 5 seconds of natural radioactivity in our detector. Of course, our acquisition window will be small. This is our large detector. So this effort started, as I told you, in 2016, and since then we've built 2 detectors, one small one with a 10 by 10 surface, let's say, readout and 1 centimeter drift, orange, and a big one, which is 24 by 20 readout area by 20 centimeter drift. This is nearly 10 liters, so it's nearly already a kind of big detector, okay? And this is called Lemon. And these are a couple of pictures. This is very cool that we built the field cage with a 3D printer. So, and these are the gems, okay? So again, these are other picture of us building up the prototype. It was very funny, I have to tell you. And also you can find us on the web, and you can find us also as this is social detector hashtag on Facebook. And so the results that were very encouraging. We started with a small prototype because, of course, it's easier to get a nice result on the small prototype, but we also confirmed that on the large one. So this is, for example, how an iron 55 event on X-ray looks in our detector. This is nearly 6 keV, so it's already low very energy, and you can see very nicely how you see this order 1 millimeter spot. Then if you compare the number of photons that you measure in this millimeter spot with the, let's say, the noises that you have in a black, let's say, spot, this is the distribution that you end up to. You see that our signal at 6 keV is very nicely much bigger than the background, okay? This, again, I'm not going to the number, it kind of implies a energy threshold of 1 keV. And all of this with about a 30% resolution. This is the common resolution that you get when you have a general amplification of charge. So this is consistent with, let's say, what is expected. Even nicer, this is the response of our detector to americium beryllium neutrons, and in general how we do particle identification. So for the first test we put a magnetic field just because we wanted to be sure which was what, no? So it was easier. So here you can see that you have this very bright track, which are helium recoils, and you also have this small Carling and also big Carling track, which are respectively low energy and high energy gammas. So what we did is that just looking at the number of photon per pixel, which is the ionization density, so the fact that these things are curved is not used, was just for us to see it, we can very easily discriminate nuclear recoil from electron recoil, and this is an example how the code recognizes the nuclear recoil with respect to the other kind of recoil. Again, this is a super simple analysis, because in order to do particle identification, you can also use the track topology and in general the track length versus energy. So this, our capability of doing this will highly improve once we improve the analysis, of course. And of course, we measure also spatial and energy resolution. I talked that. Okay. So now let's go to the big detector. This is again is 20 centimeter drift, 10 liters. So this is our 40-50 MeV electron tracks, which are kind of minimal ionizing particle looks in our detectors, and we use this to study the position resolution, and we get order hundreds of micron position resolution even along the 50 meter drift direction. So this is very nice. The other nice thing is that this gas mixture that we choose is very nice because it has a very low diffusion. Diffusion is, let's say, a way to quantify how much your image, let's say, gets spoiled through the drift. Again, without going into detail, which is very specific, I can give you later. Our gas mixture has a behavior that is very close to thermal behavior, which is the minimum, let's say, diffusion that you can achieve, and it's about 120 micro per centimeter per square root of centimeter. But the very interesting thing is that you can use this diffusion to fit and understand which is the distance from your, let's say, readout plane where the event happened, okay? Because of course, if it's closer, you will see like more defined, more crispier image. If it's far away, you will see this image a bit more fainted, okay? And so we developed an analysis, and this we can do it with both the CMOS and the PMT, that together with this, we can determine the full three-dimensional position and hence do fiducialization, so reject these bad RPR backgrounds with about 10%, 20%, where is written? 10% efficiency, okay? So, sorry, 10% of the volume that we throw out, so not very, very few volume. Again, this is the result on the large prototype for the energy threshold, still with Iron 55, and again, without going into details, is that this is consistent with what we were expecting because of the different dimension, and this is also indicated that we will have a kind of 1 keV threshold also on the final detector. We did also test with a neutron gun, and we verified our sensitivity to low energy neutron, which are much more close to the, let's say, expected energy that we have for a WIMP-like event. And we verified that we have sensitivity to the full three-dimensional reconstruction with this. So out of this came the proposal for CYGNO, which will be a 1 cubic meter detector of about 1 kilo mass that will incorporate all these features. And this is a collaboration that it's mainly come from Italy, but we have other people from, again, UK, Australia, US, joining us from the XENONT TPC collaboration. And the other thing I wanted to point out is that being atmospheric pressure and room temperature, this kind of detector doesn't need a big infrastructure like cryogenic detector, like when you have noble liquid, okay? So the timeline of the XENONT roadmap is this. So we are now at starting of 2019. We're building a new prototype, which will have, let's say, the dimension of a single module, meaning there will be a prototype which will be looked at one camera, and will have the same volume that in the final detector one camera will look at. We're already building this. I was at 7:30 having a meeting for that here, and the idea is to start constructing XENONT and installing at Grand Sasso in 2021. So the very nice news that I can give you, I couldn't put it in the slide because it's not official yet, will be next week, is that I won an ERC consolidator grant to fund this experiment, so for 2 million. So this is funded. And the idea is to use this towards a 30 cubic meter detector. The other idea is that for the first run, we want also to produce an interesting measurement, which is interesting for all the current and future experiment on Gran Sasso. And we want to do a precise simultaneous measurement of the thermal and fast neutron, because without a neutron shielding, we are highly sensitive to the environmental neutrons of Gran Sasso Hole, and we can do a seasonal measurement, which you can imagine in a place where the DAMA experiment saw a seasonal modulation of the rate can be very interesting, and I'm not saying anything. And finally, I'm ending with our expected sensitivity. You see the full line represent the 1 year, 1 kilomass, 1 cubic meter signal, and the dotted, the dashed line represent what we expect for 30 cubic meter and 3 year lifetime. All of this is assuming zero background, because we assume that we think we can have an electron-neutron, let's say, discrimination to the level to have zero background. So let me conclude with just a couple of words about the dark matter future, okay? Because there are three only scenarios, I think. So either we observe dark matter and we are all happy, but then you need a directional dark matter experiment to do dark matter astronomy. Or else we have some incompatible result. Some say they saw some signal, some say they exclude it, and we are already in this kind of situation. Then you need a directional dark matter signal to decide if this is true or not. Finally, the worst thing that can happen, we get down to the neutrino floor, we don't see anything. Then you need a directional dark matter experiment to go below the neutrino floor and see if there is something else. So I think it's compulsory to start thinking about this. So stay tuned for CYGNO birth, hopefully soon.
Thank you very much, Beta, for this very nice talk, and congratulations for the ERC Congrats Consolidated
Should
grant.
be public next week, so I thought I could say out loud.
Hi, thanks for the talk. It's a lot of stuff, but I have a very basic question.
Yes.
So why was CYGNOS, the direction of CYGNOS chosen? What's special?
No,
I
it's
mean,
not.
You must have other sources around. So.
No. It's not special. It's the way that we move around the center of the galaxy. Because the dark matter is still, okay? The dark matter stays still. Okay, dark matter stays still. You, us, all together with the solar system, we move here around the center of the galaxy, you know? And what you see in front of you moving around the center of the galaxy is the CYGNOS constellation. So that's why all these CYGNOS in this talk.
Okay, but it could be one that's just nearby as well. Or
no, it's not the dark matter come from CYGNOS.
No, I understand that you're moving in the direction of CYGNOS. That I understand.
Yes.
But you probably have other constellations that's also in the
direction.
I
mean, maybe it's more poetic. I mean, I don't know.
Okay, so there's not a particular characteristics that made you choose this constellation that we're moving toward it.
But this, I think you can ask to astrophysics people more than me. It's just a name for us.
Cancer. I mean,
it's better CYGNOS than cancer, maybe.
No, that I understand, but there's only this constellation in this direction?
I should have...
So what's the radio purity that you can achieve with these gem detectors?
Okay, we are studying this because, as I told you, we are in these R&D stages, and actually this detector that we are building now is the line detector, and yes. So we are building this detector, while keeping the name lime or whatever. This will be the idea is to test on this detector the radioactive content, to try to minimize on this detector, because everything that we built so far was also came, let's say, with what we had in the lab, so there was not a search for radio purity. This is what we are going to do now, but we already have some measurement of the gem reactivity, of the camera reactivity, and we are also developing a full detector simulation, again, together with these colleagues that are... The gems are made of copper and krypton. gems are 50 micron thick kapton with 1 micron thick copper on top of so gems actually, so for the internal part of the detector, the gem will be the higher radioactivity part, but there is also work at CERN to minimize this kind of radioactivity, for example, to replace the kapton with less radioactivity, because of course, you know, copper is kind of fine for this. So of course, we are working on this. This is a very important issue, of course, and it's something that we need to find out. But the point is that at the 1 cubic meter or scale, we can, you know also from other experiments similar like BRIT, that is the only dark matter reaction dark matter experiment existing now, that you can deal with background, more or less. Okay, so we are pretty confident we can get, also because they will be our collaborators, so we can exploit their know-how in this.
I also have a very basic question. I didn't quite get, like, what is the timeline for getting to the, you know, if you want to go below the neutrino floor, you need a huge detector.
The point is also that this is a very recent discovery for me, I didn't know, that the neutrino flow for helium doesn't fall down, it goes straight. Did you know that? I didn't know that, I'll show you. And actually it's higher than this, so actually in order to know that if you get it to the neutrino floor, we have actually, I met this guy in Zaragoza 2 weeks ago in another workshop, and we want to develop this kind of study, because the real neutrino floor would be a composition, so we have three targets, helium, carbon and fluorine. Oh, okay. So we have 3 targets, and that limit comes from the 3 targets. This part comes from the helium, this part from the carbon, and this part from the fluorine. So the real neutrino floor will be a part from the helium, a part from the carbon, and a part from the fluorine. So it's not easy to visualize or to have, you know, an easy, there will be 3-4 events. Anyway, I mean, just to say something like this about, so, yeah, I mean, like 50, so with 30 cubic meter, 3 years, we are close. Okay, but I cannot tell you how much. It's something that we are working on. Again, as I told you, it's a very new detector. But the point is that we will be able to say that this event comes from the sun and not from Cygnus or Cancer or any other constellation you like. Yeah.
So on the right plot, if I pick the line for 100,000 cubic meters, like what is the time scale for doing, but this will this be, it's not going to be one detector, if I understood correctly, right?
Okay, here Cygnus is not shown because we concentrated on the low mass region, and we wanted to compare our project with other projects in the low mass region. And here, yes, here you're showing Cygnus. Cygnus will be like the idea to have it, I don't know, 30 cubic meter detector in 5 different laboratories, summed up. It's okay. So actually, again, 100 kilo cubic meter, no, that's like, okay, whatever. The real project for Cygnus is 1,000 cubic meter for Cygnus, then 100,000, yes. Okay, it was just to show the projection.
Are you not asking a question to yourself?
Maybe. I can ask. I have a lot of questions to myself.
Okay, so in the meantime, we thank you very much again for your talk, and congratulations again. Okay, so the session is over. We now have the coffee break, and we reconvene at 11:40.